All right. We're going to do a little problem involving the velocity-dependent force. Got a metal ball with a mass of 50 grams is released from rest within a fluid after a time of 0.180 seconds. The object speed is 55% of its maximum. We want to know what is the time constant of the system. We want to know what is the object's speed after 0.310 seconds. What is the terminal speed of the object, and at what time is the magnitude of the resistive force equal to 0.350 newtons? So we just start off with the first one. We've got ourselves, number one, that's not going to work. We've got ourselves a mass of 100 kilograms, right? So we got ourselves 0.05 kilograms there. And we're told that at t is equal to 0.180 seconds, v is equal to 55% of its maximum speed. V is equal to 0.55 v sub t. So, with this, we have ourselves that v of t is equal to v sub t times 1 minus e to the negative bt over m. So, what do you need to do? You need to figure out what is the time constant. So we can go ahead and rewrite this a little bit in terms of the time constant, because this is equivalent to saying v sub t times 1 minus e to the negative t over a tau. And we want to solve this out for tau. But we also need to know what the terminal speed is, or at least have to have some manageable way of rewriting it. So we should note that v sub t itself was mg over b, and m over b is what tau is equal to. So we can rewrite v sub t as being equal to g times tau. So, there we go. However, it ends up not being necessary. I'll show you why here momentarily, but this comes in handy here and there. At any rate, we've got that v of t is equal to 0.180 seconds, that we have 0.55 v sub t, and v of t is equal to 0.180 seconds is equal to v sub t times 1 minus e to the negative 0.180 divided by tau. So this has to be equal to this, and thus we have ourselves that 0.55 v sub t is equal to v sub t times 1 minus e to the negative t over tau. And really this t here, let's just go ahead and put in 0.180 seconds there. All right, so we got v sub t cancels out. That's our normal rate. Goes away, and we're just left with this being the fractional value of v sub t, which is 0.55 in this particular case. So 0.55 must be equal to 1 minus e to the negative 0.180 divided by tau. Yeah, that has seconds in it, so does tau. Nonetheless, we go ahead and solve this out. We want to isolate tau there, solve for it. We've got to get rid of the exponential. Can move some things around here really quick and write this as e to the negative 0.180 divided by tau is equal to 1 minus 0.55, which would give us 0.45. Getting rid of the exponential, take the natural log of both sides, and we've got ourselves negative 0.180 divided by tau is equal to the natural log of 0.45. And thus, tau is then equal to, move tau over there, this over here, we got negative 0.180 seconds divided by the ln of 0.45. And at that, grab my calculator that I have moved. There we go. we've got 0 by 0.45. Gives us 0.225, we'll call it. 0.225 seconds. There's the time constant of this particular system based upon achieving 55% of its maximum speed over a time of 0.180 seconds. Once we know the time constant, we know how this system evolves. After one time constant, which would be 0.225 seconds, it'll have 63.2% of its max speed. After two time constants, which would be 0.45 seconds, it has about 86.5% of its maximum speed. After three time constants, 95, and so on and so on. After 10 time constants, we can assume that it is or has achieved its terminal speed, which would be 2.25 seconds. So some valuable information embedded there with that tau. And that's why I want to know what it is. So there is the time constant of the system. We also want to know what is the object's speed after 0.310 seconds. So we come over to a nice little part B, and we say V of t is equal to 0.310 seconds is going to be equal to V sub t times 1 minus e to the negative 0.310 divided by tau, which we already know to be 0.225. Seconds divided by seconds, unit list over there, and well, we've got something. We've got a V sub t here. Well, again, we could calculate what it is, which is asked in the next part, or we can just go ahead and sub in g times tau, and note that V t is equal to 0.310 seconds is equal to g multiplied by 0.225 seconds multiplied by 1 minus e to the negative 0.310 divided by 0.225. This gives us ourselves 1.65 meters per second. Here we go. There's the speed of this object after 0.310 seconds. Let's check something out here. Let's look at this next question, which is really easy to answer at this point. What is the terminal speed of the object? See, we want to know that V sub t is what? Well, it's equal to g times tau, which we've already done. 8 times 0.225 gives us 2.205 meters per second. So there's the maximum speed of this object. After 0.31 seconds, we're going 1.65 meters per second. How much is that? It's not quite this, right? We still need another 0.6 meters per second to get up to this. So start thinking, is that reasonable in terms of time constants? Well, this is going to be between 1 and 2 time constants. One time constant is 0.225. Two time constants would be 0.45. So we should be somewhere in between 63.2% and 86.5% of the maximum speed. In which, yes, 1.65 is in between that range of the maximum speed of 2.205 meters per second. If it wasn't, we'd have done something wrong. Go back and figure it out. But it's good to make good correlations there with the time constant and other quantities that you can interpret via the time constant. Last question. At what point in time is the magnitude of the resistive force equal to 0.350 newtons? All right, let me make a little bit more room here really quick. Let's just move this one down. Up. Right here. And what do we get out of this? Well, we're told the magnitude of R is is going to be 0.350 newtons. And the magnitude of R is going to be equal to V times the magnitude of V. Forget the negative sign because we're just talking about magnitudes here. So really, the question ends up becoming still, at what speed does the object substantiate a resistive force of 0.350 newtons? Of course, we need to know what this coefficient of proportionality is in this particular case, which again is easily extractable. So what we can do with this is start expanding things out a little bit, making some better sense of stuff. Let's just go ahead and figure out what B is first. We've got that tau is equal to m divided by B, so B is going to be equal to m divided by tau, which is 0.05 kilograms divided by 0.225 seconds, which we could calculate really quickly to be 0.222. 0.222. And what would the units of that be? Kilograms per second. So there is our coefficient of proportionality. And now we want to know when is the resistive force equal to 0.350 newtons. So we've got ourselves that, how do we want to write this out? How about just like this? 0.350 newtons is equal to B times V. B is just some constant, but V is what has the time variance in it. So we have B times V sub t times 1 minus e to the negative t over tau. V times V. So what can we do with this? So we can go ahead and start thinking about isolating t once again. Or not once again, before it was tau. No, we isolate t. So we can divide both sides by b and v sub t, and write this as 0.350 newtons divided by b v sub t will then be equal to 1 minus e to the negative t divided by tau. We know what tau is, we know what b is, we know what v sub t is. This just resolves into doing a little bit of algebra, not too bad here. So let us do that. We'll further write this out. I'm just going to isolate this little term right here. We can solve everything out afterwards. We can write that e to the negative t over tau is equal to 1 minus 0.350 newtons divided by b times v sub t. Take the ln of both sides. We've got ourselves negative t over tau is equal to the ln of 1 minus 0.350 newtons divided by b times v sub t. And then finally, we can multiply both sides by negative tau and get ourselves the t is equal to negative tau times the ln of the quantity of 1 minus 0.350 newtons divided by b times v sub t. It's a little mouthful there. All right, so we'll come on over to this portion right here, put in our values, and let's solve this out. We've got t is then going to be equal to negative 0.225 seconds multiplied by the ln of 1 minus 0.350 newtons divided by b, which was 0.222 kilograms per second, multiplied by v sub t, which was, I erased it, but it was 2.605. So, let me make sure here. We've got 2.205. Wasn't a big mistake. 2.205 meters per second. Span that out there. And this is what we've got. So we'll have that the resistive force is equal to 0.35 newtons at a time of 0.225 0.2826. There we go. Could we check this out and make sure that it's reasonable? And the answer is, sure we could. What is the maximum resistive force? R max is equal to mg. The maximum resistive force occurs when the velocity substantiates enough to having the gravitational force being equated with the resistive force. So in this particular case, the max would be 0.05 kilograms times g, which 0.05 times 1.8 gives us about 0.49 newtons. So we're looking at 0.35 newtons. That's a little bit more than half, right? A little bit more than half. And what are we? A little bit over one time constant. So we should find that 0.35 is over 63.2% of 0.49. I'm going to just set up the ratio really quick. 0.35 divided by 0.49. And we get, that is 71.4%. After one time constant, we'd be at 63.2%, or a little over one time constant. And yeah, we're over 63.2, we're at 71.4%. Done. Makes sense? Check. So, that's it.